Now that you've seen a little bit about how downscaling works kind of in a specific application, see a little bit about how that works at the pixel or the raster level here on the left-hand side, we got our big climate data emission scenarios. And we've got some of the input data going into that. Elevation data. Elevation is important for climate. And so on the left-hand side, we can see this emission. It's part of the input into the emission data, let's say. And so this global climate model has huge pixels, degrees by degrees, 100 to 250 kilometer scale data. Wild. So the Alps, or the European Alps there, are basically represented by one big pixel. One pixel of 100 to 250 kilometers in size. Wow. 3.75 degrees by 2.5 degrees. Incredible. Well, you could downscale that, do some kind of statistical work to get that into a 25 kilometer pixel, and likely using some other data to help inform that. And then you have reality, I love the double quotes there, in some kind of surveyed or actual local or real data there. Now, we cannot do a global climate model at reality or local scale data, because I don't know if there's a supercomputer out there that could handle, say, 1 meter pixels for the entire planet for one data set. Oh, wait, you mean there's more to climate data and climate modeling than just elevation data? Tell me more. So we use these different downscaling techniques to take things like global models and turn them into regional models, or to understand the relationships between how global output works on a, say, climate versus how that will impact in regional cases. Here's another case, another YouTube video linked. I don't have that separated out, but you can imagine how for a climate model, does treating the city and county of Los Angeles on this left image as essentially 2 pixels, part of LA goes into those other 2 pixels next to it. But so we've got California. And if you look at that extra outline about 35 degrees north and 118 degrees west, that's LA. And then we zoom into it left and right. Do you think treating LA as 2 pixels worth of elevation versus treating it as all those pixels of elevation is actually going to have a difference in terms of how you understand climate in Los Angeles? That's right. The answer is yes. There's this wonderful little mountain range in LA, the San Gabriel Mountains. And it actually snows on the San Gabriels fairly regularly. Doesn't snow in LA fairly regularly. Elevation is a wonderful thing. Well, I guess maybe it used to snow regularly. I don't know how things are anymore. But that difference in terms of climate modeling really plays a big part of understanding how something like estimating global climate change will actually draw down to working at a local scale. So downscaling is quite interesting, quite fun, and a really fun, say, puzzle to think of in your brain. I'm going to wrap up our talk about raster data here before we move on to remote sensing, just by talking about some data types. We've talked about data types before: nominal, ordinal, rational, interval, rational, ratio, interval, nominal, ordinal, ratio, interval. There we go. Well, this is data that's, these are another way of understanding data types. So again, we say data type, we mean a whole bunch of different stuff. So in this case, the file format is raster. The structure is pixels arranged in a grid, and we have continuous and discrete data. Continuous data represents some kind of constant surface. Could be floating point, could be integer, doesn't matter. Have topography, you got continuous data. Everything has an elevation, and any elevation value is possible between the bottom elevation value and the top elevation value in your given scene. Again, floating point, integer, either is fine. Raster data can do floating point. Don't let anyone tell you it can't. Just increases the file size. And any of these different types, topography, rainfall, precipitation, satellite imagery, proximity to something, think of a bunch of other stuff, continuous data. Well, raster data can also be discrete. It can be limited to a set of values, or it can be classified. It could be classified down to binary data. Yes and no, good or bad, suitable or not suitable. Land cover classification is often this way, and land suitability, presence, absence data for like species models, snowfall, all of that, discrete raster data. So we have continuous data and we have discrete data. You can tell that little map, one of those is continuous, one of them is discrete, but we can shift one direction. So if we have elevation data and we want to classify it into bins, into groups, 500 meters, 1,000 meters, so on and so forth, we can do that. It's great. It's easy. It simplifies our data set. We can never go back. Continuous data turns into discrete data, and then we have discrete data. If I just gave you discrete data, you could never recreate the original continuous data set. How you work with your data matters a lot. So you might say, well, why did I make discrete data if it loses all the fidelity and detail and interest of the continuous data? Maybe you don't need that detail. Maybe you don't need that interest. Maybe you just need groupings of elevation at 500-meter intervals. Maybe you just need to know which elevations are good or bad. And that's great. You can save yourself a lot of processing time if you cut it down to simple groups. So it comes down to, once again, knowing your data, understanding what you have, and understanding how you do these things. And always keeping backups of the originals. We can do all of this work with a lovely tool called the Raster calculator. You will get to learn and practice that Raster calculator in Lab 7. And there is a great fundamentals video. It is in the old ARC, but that's okay. With Esri Education Manager Joseph Kursky. He makes great videos about GIS. I like to call Dr. Kursky the Bill Nye of GIS, I think is the appropriate way to describe him. So if you're interested more in how you can do these calculations, check that out. Maybe you'll do it in the lab. One last video for us today, or in this sequence of recordings, we're going to talk a little bit about remotely sensed data, because that comes as rasters. I've referenced this a lot. We should have a fundamental exploration of how it works. See you in remote sensing.